Hello everyone, welcome to this channel of easy study of food technology and engineering. So today's topic is heat transfer in food processing. Here we'll discuss the theory part, and in the next video we shall solve some numerical problems related to GATE exam. So what is basically heat transfer? The movement of thermal energy or heat from one place or from one body to another body is known as heat transfer. Heat transfer occurs in three kinds of mode: conduction, convection, and radiation. So conduction is basically that is the transfer of heat by direct contact, and this happens in solid where the molecules don't move but the vibration of the energy transfers the heat. Next point is convection. Convection is the transfer of heat through fluid motion. Fluid that is in liquids or in gases. Next is radiation. Radiation doesn't require a medium, so here the transfer of heat happens through electromagnetic waves. So the definition of conduction is heat transfer occurs due to the transfer of energy between the adjacent molecules or atoms, and it happens primarily in solid particles where the particles are closely packed and energy is transferred through vibration or collision. And metals are good conductors. Okay, so conduction happens fast in case of metals, and conduction is governed by uh, an equation or law that is known as Fourier's law. And Fourier's law states that the rate of heat transfer through a material is proportional to the negative temperature gradient and the cross-sectional area perpendicular to the direction of heat flow. Mathematically, it can be written as like this, where Q is the heat transfer rate, uh, A is the area, and delta T by delta X is the temperature gradient. Negative sign because when delta T increases, that means the thickness is decreased thickness, and when the thickness is more, delta T will uh, decrease. That is why this negative gradients come. And here K is known as the thermal conductivity. So what is thermal conductivity? So thermal conductivity is the heat that passes through per unit of area and per unit of temperature gradient. Okay, and the unit of thermal conductivity is watt per meter Kelvin, or you can write as degrees Celsius also. This is the unit of thermal conductivity. You can get the definition of thermal conductivity from the previous equation. So in case of insulators like air or wood, the thermal conductivity is very low, but in case of metal, the thermal conductivity is high. So the in and the factors which like influences the heat transfer in conduction is first is temperature difference, then thickness of the material, cross sectional area, and thermal conductivity. So next is convection. So what is convection? Convection is the heat transfer that occurs in fluid, and this occurs due to the bulk movement of the molecules. Okay, so if it is by there are two kinds of convection. One, if it is due to the natural forces, that is the buoyant forces, it is known as natural convection, or an external force like pump, if we put there the because of which the molecules move, that is known as forced convection. So convection is governed by Newton's law of cooling that states that the rate of heat loss of an object is directly proportional to the temperature difference between them, and it is expressed as Q equal to H, which is the convective heat transfer coefficient. A is the area of the object, and this are the two temperature differences. and the unit of H is watt per meter square Kelvin. So the difference between thermal conductivity and the convective heat transfer coefficient is an extra distance square. Okay, but you will see that the unit of heat is will be always similar, that is heat rate is always watt. Then radiation, which happens due to the electromagnetic waves from a surface. So all objects like will emit a thermal radiation when light falls on them. Okay, so this is and radiation is governed by Stephen's Boltzmann equation that states that the total energy radiated per unit surface area of a black body is proportional to the fourth power of the absolute temperature. Why black body? Black body is considered as an ideal body in heat radiation because it is uh, assumed that black body emission is zero and absorption is complete. Okay, E is the radiated energy. Here E is radiated energy. We can also refer to as Q, and T is the absolute temperature, and phi is the Stefan's Boltzmann constant. Sorry, sigma is the Stefan Boltzmann constant. So let's take an example. So here an electromagnetic energy is being generated here. So this is the radiation from where heat is being gone. So when it reaches the bottom of the pan, so from bottom of the pan to this the other side of the pan where water is there, the heat reaches through the mm, through the mode of conduction, and also to this metallic handle the heat is being transferred through conduction, and then after that where from the surface of the pan to the water molecules it is reaching by convection, that is the movement of molecules. So this is a overall application of the three modes of heat transfer. So in food processing, where does this theory is mostly applicable? In thermal processing like pasteurization, sterilization, then also in case of freezing and chilling because that is also heat transfer, then drying, which is a very basic food processing operation, baking and roasting, and heat exchangers. Heat exchangers where fluids are being heated or cooled. mm, Cool. So this is mostly used in case of pasteurization, heat exchanger. So the theory of heat transfer is applicable in this kind of application in food processing. And I'll discuss some of the, since these are brief notes, I'll discuss some of the important formulas. Okay, that usually numerical problem come in gate, and the formula that are very important is like already I have discussed conduction, right? So conduction through a slab is already being given. So when it is and like geometry wise this uh, conduction differs, the resistance, the flow differs. Okay, so in case of sphere it is radially happening, in case of cylinders it's like the logarithmic mean of the your total surface area, in case of slab it's just the thickness difference. Okay, so here I have shared the formula for slab, that is Ka, that K is the thermal conductivity, A is the your area, delta T1 T1 minus T2 is your temperature difference, and L is the thickness of the slab. So when it comes to cylinder, we get a twice pi KL, that is your the longitudinal cylindrical area. Okay, and there is in the denominator we'll see logarithming of r2 by r1. So r1 is the inner diameter and r2 is the exterior diameter. Okay, and the temperature difference remains same because the temperature difference is the your driving mechanism of heat transfer, and all the other things as we can see the thermal, these are the your thermal resistance. So the thermal resistance will vary for your cylinder, then for spare also it will vary. So this is for just one one cylinder or one kind of slab when there is uh, only two sides. But if it is a composite slab or a composite cylinder which has many layers, then the resistance will be the total resistance. First, we'll calculate the resistance of this part, then we'll calculate the resistance of this part, then we'll calculate the resistance of this part. Similarly, for cylinders also, first we'll calculate the resistance of the inner one, then the outer one. Okay, in this, so here the total resistance is being given, like when we will sum up of each of the layer we'll get the total difference, and in this way we can calculate the heat transfer. This concept will be clear in the next video when we'll practice some problem. Next, one more important is your lump capacitance model. We use this when there the all the equation which we were discussing were in the steady state heat transfer, because when unsteady state heat transfer comes, then there comes a time factor. So that means that temperature will keep on changing with respect to time. So one important formula is lump capacitance. Lump capacitance, it discusses that delta T by delta T, that is the rate of heat transfer, there's a temperature, uh, assumes that the entire object has a uniform temperature, and this is mathematically expressed as in this manner: delta T by delta T, that is temperature by time, is equal to HA by rho CV, that is, and then the temperature difference. T is the your object's temperature, and uh, T infinity is your ambient temperature. C is the specific heat, V is the volume, and A is the area, surface area, and H is our convective heat transfer coefficient or heat transfer coefficient. So when we have to calculate unsteady convective heat transfer, we'll use this formula. But there's another concept to this formula, is this: this formula is only applicable when Biot number is less than 1. Biot number is what? It is a dimensionless numbers that compares the internal thermal resistance to the external thermal resistance of the body. This H is your convective heat transfer coefficient. LC is the characteristic length. Characteristic length matlab volume divided by area, and K is the thermal conductivity. So if Biot number is less than 1, so it suggests that the temperature within the object is uniform. Okay, so we can use this formula. But if Biot number is greater than this one, we can't go with this formula. That is a more complex problem, and we have to opt for like numerical methods, partial differential equation solve method. So that method is complex, and we generally does those question doesn't come in gate exam. That is for higher levels. The next important concept is heat exchangers. So heat exchangers, the two kinds of a hot fluid and a cold fluid keeps on flowing. So which the cold one will get heat, will absorb the heat energy, the hot one will release the heat energy. In this way the fluids are being cool. Like for example, in case of chilling of milk, very chilled water is sent to it so that the milk cool downs, and again in case of pasteurization, a hot fluid is passed through it so that the milk gets pasteurized. Okay, this kinds of, so heat exchanger are of two types. One is your parallel flow, one is your counter flow. So parallel flow means, suppose if the hot fluid is entering from this side, that means the cold fluid is also entering from this side. Okay, this is the hot fluid. Suppose T TH TH dash. Okay, and this is suppose the cold fluid. Okay, this is the cold. Let's assume is it as TC1. So this temperature difference, the inlet temperature difference is your delta T1, and the outlet temperature difference is your delta T2. Now in case of counter current, if the hot fluid is flowing through this side, that means the cold fluid will come from this side. The entry of the cold fluid will be from this side. Okay. So this one will be your delta T1, and this one will be your delta T2. So this is the LMTD, that is the your logarithmic mean temperature. Okay, and in this way we can calculate the overall uh, heat transfer occurring in a heat exchanger. This is same to the our convective heat transfer formula, and here U is the overall heat transfer coefficient. So thank you for listening. In the next video we shall solve some numerical problems related to this. So keep watching this channel for short videos.